Okay. Is everybody seeing that it's recording? Great. All right. Let's start again. So welcome to this year's first semester seminar. Our speaker is Nadav Meir from the University of Wrocław. And he will tell us about pseudo-finite sets and pseudo-o-minimality.
Right. Okay. Thanks, Patrick, and thanks. Thank you very much for having me. Thanks for the opportunity to talk in front of this esteemed audience. Yeah, I wanna maybe start by saying that this my research that presented in this talk is part of my PhD thesis. It's okay. It's also to appear in the Journal of Symbolic Logic. It's part of my PhD thesis done in Ben Gurion University under the supervision of Asaf Hassan. And it was motivated by a question asked in a workshop on tame geometry by Philip Ranami. So that's the acknowledgements. And yeah, I want to say that also I'm really far from an expert in this field. Obviously, you know, there are people here. I can see that even I'm going to mention some of the names here. So, so yeah, I mean, feel free to comment whatever there is to comment. But nevertheless, this is your first talk after a Christmas break, so I'm going to make this kind of a smooth transition. So this talk is not going to be very technical, but even though I'm far from an expert in the field, I did kind of getting into it, develop a point of view about things that I'm going to also present this point of view. But yeah, it's also only my humble point of view. So I would love if people could also, yeah, maybe just feel free to jump in and comment and whatever. Okay, so I guess, yeah, the audience, I'm not sure how, oh, wait, how do I stop annotate? For some reason, I'm stuck on annotation. Do this. Yeah, okay. So, yeah, I guess I can go through the definition of o-minimality very quickly. I guess this is something that's very familiar to everyone here. Correct me if I'm mistaken. So whenever I consider an o-minimal structure, it will be an expansion of a dense linear order without endpoints. So we have all of these classic examples like the field of the ordered real field of reals. This is Tarski-Seidenberg theorem, and obviously a reduct of it, which is just an order divisible abelian group or just a dense linear order. And then there are these classic results that if we expand the field of reals by all analytic functions restricted to a compact set, then it's so minimal. And also if we expand it by the exponential function, results by Van den Dries and Wilke respectively. And there is this classic result by Knight, Pillay, and
Nadav,
yeah.
Immediate question. So
Yeah,
what does
sure.
it mean, order without the endpoints? Doesn't it contradict to the example by Van den Dries on functions restricted on the interval?
I mean just that the underlying set is ordered and densely ordered and unbounded. So if you take the reduct to the language, if you take only sets that are
okay, so
with the order, then it's
in the structure Rn, R analytic, you mean that the functions are restricted on intervals,
yeah, sure,
and not the structure.
Yeah, sure. The functions are restricted to a compact. So
Okay.
so you take all of the structure of the field and add all analytic functions restricted to a compact set.
Okay, thank you.
Yeah, sure. Thanks for the question. And there is this classic result that o-minimality is preserved under elementary equivalence by Knight, Pillay, and Steinhorn, essentially saying that, yeah, o-minimality implies strong o-minimality in that sense. And we have these nice classic facts, that is the monotonicity theorem and the Celtic composition theorem. So I just stated them. Yeah, whenever I have a definable function on some open interval, we can partition that interval into finitely many intervals such that on each interval, the function is either constant or strictly monotone and continuous. And also we have the Celtic decomposition theorem, which I don't really want to get into what exactly cells are, but they are these sets which, yeah, so I saw that in this seminar, actually, before your Christmas break, the talk mentioned, definable sets in o-minimality and the cell decomposition theorem. So I wonder if, I think it's something that's familiar to the audience in this seminar, right?
It probably is, yeah.
Yeah, so yeah, just for this talk, I guess I'm going to, because I'm working in the, from the logic point of view, I'm going to refer to like definable sets. From the logic point of view, definable in some first order language. Yeah, equivalently, you can say that an o-minimal structure is a structure with an underlying set and subsets of the power sets of that set that are closed under finite unions, intersections, complements, and projections. So that's like the other way to view it. And in the logical sense, yeah, you can take all of these to translate to and or negation and quantifiers, right? So I guess this is something that is well known. And yeah, now that we talked a bit about o-minimality and presented these classical facts and yeah, I guess all of you know already the vast impact that this field has had. And let's go over to like a philosophical discussion a bit. So I want to quote Alexander Grothendieck from A Sketch of a Program. That's the translation to English, and I am sorry for the French speakers. I'm going to say it in English because my French is comme ci, comme ça. So yeah, so he says, my approach towards possible foundation of tame topology has been an axiomatic one, rather than declaring that the desired tame spaces are semi-analytic spaces and then deploying constructions and notions which are familiar from topology. I prefer to work on extracting which geometrical properties of the semi-analytic sets in space Rn make a notion of tame space, and what hopefully makes this fundamental notion for a tame topology, which would express within the topological intuition of shapes. So as I've read from several reviews, I guess, on o-minimality, this is kind of the, so yeah, probably too young to really know, but I guess this is what I've read, that the o-minimality is logic or model theory's answer, right, to Grothendieck's question, kind of this axiomatic approach towards tameness of the semi-analytic spaces, or the way that the semi-analytic sets behave in R to the n. Yeah, but okay, so now maybe, yeah, the point of, I guess, the point of view that I will kind of, I want to convey throughout this talk is that the job is not completely over or done. So yeah, let's go over some other possible, right, axiomatic approaches to tameness, tameness conditions that are also legitimate, I guess. So yeah, this is the definition. So now I'm going to present a few generalizations. So something that you could consider as tame, but they are generalizations of o-minimality, and they are first order, as opposed to o-minimality, which is, okay, we cite it is an elementary property. It's preserved under elementary equivalence, but it's not preserved under taking ultra products, for example. Or, yeah, so it's not preserved under ultra products. It's not a first order condition. You cannot express it in a first order scheme, right? So we want to kind of extract a few properties which you can express in a first order scheme, which generalize on o-minimality, and then see that also, yeah, these properties have some well behavior for themselves. So one first example, I guess, is an example by Chris Miller. So Chris Miller defined this, in 2002, he presented the property that's called the intermediate value property, or IVP. So an ordered structure, and throughout this talk, all ordered structures will be an expansion of a DLO. So meaning that the order is dense, i.e. for between any 2 points there is another point, and unbounded. So for any point there is a point above it and below it. Yeah, so an expansion of a dense linear order has the intermediate value property if whenever I have a continuous definable function on a closed interval, and that takes on all values between f of a and f of b. So you can see that yeah, this is a first order scheme, right? You can express continuous using the order, and you can express taking all values. So yeah, any expansion of the reals, right? So because the reals are complete, then any expansion would take yeah, intermediate value property. Any minimal expansion of just a dense linear order without endpoints, because this is a first order condition that holds for minimal structures. And also, yeah, you can take as kind of, I guess, exercises to show that if you take the rationals with the order plus and a unary predicate for z, so add to the language that z is definable, that this property holds, and it's also preserved obviously under elementary equivalence because it's a first order condition. And another example that Chris Miller gave in his paper. All right, so this just follows from elementary equivalence, because you can see that this Q expanded by Z, yeah, it's just any divisible subgroup of the reals that contains one. Yeah, then this is actually elementarily equivalent to this. So yeah, also, yeah, you can take it as an exercise. So yeah, any questions or maybe comments up until now? Guess not. Right. So, yeah, already this definition is quite interesting, right? So in his paper, right, Chris Miller gives a lot of nice properties of structures that, in which the intermediate value property holds. So you can see that it's enough to assume that. So, for example, I'm going to just present one proof just to demonstrate how, I guess it's, well, okay, according to my point of view, I guess the genius in that paper is presenting the axiom and just presenting the results. But if you give the paper to any like advanced undergraduate student, or maybe a graduate student starting that, then that student can, you can give it pretty much any proposition there as an exercise to fill. So for example, this proposition, right? So if you have the IVP, then intermediate value property and a definable subset, then it has an infimum and a supremum. So to prove it, like, let's say, assume that it is bounded from below, same symmetric argument works for above, right? So to show that the infimum exists, let's look at A prime, which is the kind of the convex hull of A together with plus infinity, right? So if we have an infimum of A prime, we also have an infimum of A. And then, okay, if we have either a minimum for A prime or a maximum for the complement of A prime, then we are done. Otherwise, they are both open. And then we can define a continuous function that sends the one open sets to some A and one open sets to B. And then this contradicts the intermediate value property because there is no, doesn't have all values between A and B, right? And I guess the same similar argument you can show that also. Yeah, you can kind of use a very similar argument to also show this. So we say that a set is definably connected, right? If there are no open disjoint definable subsets of it, and the same, a very similar argument can show that actually being definably connected in a structure that has intermediate value property is the same as being an interval, and it's the same as being convex, right? So, and also actually, yeah, this actually is, you can also show that that it's equivalent to it, right? So that proposition in the slide before. So, yeah, this kind of proposition says that we call, right, a structure definably complete if the supremum and infimum exists for every bounded non-empty definable subset. And for some reason that is, I'm not aware of, because probably it was long before I even started doing any research, this term kind of took on grounds and became more prevalent among the community, I guess, but it's the same. So, so an order structure has the IVP if and only if it's definably complete, if and only if intervals are definably connected, sorry, if and only if the structure itself is definably connected. So
may I ask a question? Probably a stupid question, but I think I missed something. So you before as a structure with IVP, the rationals, right? If you add C,
let's go back here. Yeah, this one.
Yeah, this one. So and right, it doesn't have an inf, right? Because the set of all point such that the square is less than 2. So the infimum, the supremum, I don't know, is the square root of 2, right? So
yeah, sure, but
where am I wrong? So I'm wrong, right? I'm missing.
But no, because it's not bounded. So every subset, every definable subset has an infimum and supremum, including maybe plus and minus infinity. Right? So,
no, but let's look at all points such that the square of them is more than 2 and less than 3. So the infimum should be square root of 2, and the
no, but on this structure you don't have squares. It's just the additive group.
Oh, okay. It doesn't contain the products. Okay, yeah, okay. Sorry, thank you. Okay.
Yeah, no problem. Okay, so yeah, so already with this definable completeness, that yeah, now I'm going to, yeah, so we also have this nice results, which I'm not going to prove, but also everything that I presented now you can do as an exercise, and I'm sure you're going to, everyone in this audience can prove it by themselves. So yeah, so for example, definable and continuous functions from a closed and bounded set satisfy that the image is closed and bounded and definable, obviously. Yeah, if the function is injective, then f maps A homeomorphically onto f of A, and every subset of the image that is definable is closed if and only if its preimage is closed. And yeah, for every G from the image to any other image, then G is continuous if and only if the composition is continuous. So yeah, yeah, okay. So we see that already this is kind of, I guess, the first definition that I wanted to present, and already this definition is quite interesting on its own, and yeah, generalizes o-minimality. And yeah, we also have so from now on I'm going to refer to the intermediate value property as definable completeness, just because throughout these recent years, so in particular, like for example, the work by for Nasero and Economy, that they defined it as definable completeness. And they proved, so for example, this dichotomy theorem, that if we have a definable complete expansion of an ordered field, then either the image of any definable discrete set is nowhere dense, or K defines a discrete subring. So we have kind of recently this dichotomy results. And yeah, now I want to go over to another first order definition that generalizes o-minimality, but yeah, beforehand, if there are no questions about this, I guess, or comments from some people, because obviously there are people here that are much more experts than I am in this field. Okay, I guess not. So we will move on to local o-minimality, and I see also that in the audience there are people who worked in this field, right? So we say that an expansion of a dense linear order without endpoints is locally o-minimal if for any definable subset in any point there is, oh, sorry, this should be, M should be R. My mistake, sorry. So how do I do this? Should be, yeah, I guess, yeah, this should be R and this should be R because, yeah, typo there. So, yeah, whenever I have a point, there is some interval I, right, that contains that point, such that on I, right? On I, you could say that the structure is o-minimal in a sense. So on I, the intersection of but it is with, notice that it is not a uniform definition, right? It is with respect to a chosen subset A. So given a definable subset A, you can find an interval for which, right, on that interval, A behaves in an o-minimal way, namely that the intersection of A with I is a finite union of intervals and points. And you can see that this, this property is also a first order scheme, because you can actually make you can make the interval small enough such that actually, right, I'm going to, let's say you have the point A here, right? So you can, if you have an interval I such that the intersection of A with I is a union of intervals and points. So you can make the interval small enough such that A intersect I is exactly right on this ray. It's exactly either empty or the whole set, and on this ray, it's either the whole set or the empty set, right? Is that clear why it is actually a first order scheme? Yes, maybe just if I could get like maybe 1 or 2 nods from the audience, I'll see that, yeah, okay. So clear all of the drawing and move on. Okay. So yeah, right. So in an analogous way to the monotonicity theorem from o-minimality, we have an analog result for local o-minimality by Anton Giulio Fornasevo, which proved that if I have a definably complete locally o-minimal structure, and I have a definable function on an open interval, so it's imported now that it's an open interval with endpoints in the structure, not plus minus infinity. Then there is a closed, bounded, and discrete definable set A, such that on each interval X and the successor of X, where X is from that definable discrete set, right? So it's discrete, so we have the successor function. The function is either constant or strictly monotone and continuous. So I want now to recall the name of the talk. That is, it has pseudo finite sets. So this is kind of a tease to what is going to come. So these closed, bounded, and discrete definable sets, notice that in this case, in local o-minimality, they take on the role of finite sets in o-minimal structures, right? Because in an o-minimal structure, you have a finite set such that between any 2 points, you have this constant or strictly monotone and continuous. And here, it's replaced by closed, bounded, and discrete. So yeah, so now you can kind of start thinking, yeah, I guess if you take an ultra product of o-minimal structures, and then you get a locally o-minimal structure because local o-minimality is a first order scheme, so it's preserved under ultra products, and then you get this condition, and the ultra product of if you add like a predicate for a finite set in each of the structures, then in the ultra product, it will definitely be closed, bounded, and discrete, right? So you can say that a pseudo-finite set in this sense is, in a sense, an ultra product of finite subsets, right? And we will review this maybe a couple of slides. And yeah, another definition, now we come into the definition by Hans Schoutens, that defined type completeness. So the type completeness is local o-minimality together with essentially local o-minimality in plus minus infinity. So in addition, any definable subset, for any definable subsets, there are open rays in minus infinity C1 and C2 plus infinity, such that yeah, on that interval, either that interval is strictly contained in A, or its intersection with A is empty. So yeah, you can see that this is exactly adding the local o-minimality condition for kind of the points in plus minus infinity, right? And we have a very similar result from Schoutens to the results from
Nadav, can you give an example of something like that?
Yeah, so it's a good question, actually. Yeah, I can't recall now, but I mean, okay, so so yeah, I think like, okay, so for example, right, if you take this example that we talked about in the definable completeness, right, about the IVP. So the additive group of Q with the order and Z, and I think, yeah, that should be also yeah.
It cannot be with Z. You cannot have Z at infinity.
Oh, right, because you have the types in plus minus infinity, right? So yeah, well, okay, so that is locally or minimal, but it's not type complete, I guess. And then to get type completeness, well, first of all, okay, you can take any ultra product of or minimal structures, but that's quite kind of a cheat. Yeah, well, okay, actually, maybe if we have time, I will look in the paper of Schoutens, but if I recall, actually, he didn't also give. I don't remember if he actually gave an explicit example in his paper, so it's an interesting question.
Could you add a pseudo finite set to a divisible order abelian group?
Yeah, okay. If you add,
we would need to produce the finite set, but
yeah, okay. So that's okay. So first of all, yeah, you can take just an ordered structure, just with the order, and add a pseudo finite. So add a closed, bounded, and discrete set. That would be type complete. And then if you want also an algebraic structure, so you want maybe a order divisible abelian group, well, okay. This comes down to the fact that I'm not sure how, like, you need to add this definable subset, this predicate in a delicate way, or somehow, which I think I will discuss it in the end of the talk, but it's not clear to me, at least. Maybe there are people here which will have an idea, but it's not clear to me whether yeah, how easy it is to just take an order divisible abelian group, add a predicate for a pseudo finite subset, and then would it be type complete? I think you need to do it in a delicate way. I don't know. You need to do some accounting, right, in order for it to work. But, yeah, but maybe I will discuss this in the end of the talk a little bit. Right. Yeah, okay. Yeah, also, I mean, maybe you can think about ad hoc examples if you take an ordered divisible abelian group, let's say Q, and then add like a predicate, unary predicate, and in one structure define it as 1, and the second structure define it as 1, 2, and so on and so forth. And then take the ultra product and then figure out what comes out of it. That would be definitely type complete, but I'm not sure how explicit. Yeah, how explicit that. Well, it's not explicit, right? But what is the structure there? But yeah, anyway. If there aren't any more questions or comments, I'll move on for now. Right. So just I wanted to say that this theorem is the same as the result by Fornaciero, just that the function now can be defined on all of the structure, not only on a bounded interval, right? So yeah, and then we can see that actually Schouten's proved that definable completeness together with type completeness is equivalent to an analog statement of o-minimality, but taking a disjoint union. So every definable subset of the line is a disjoint union, maybe infinite, right, of open intervals and a single discrete set. So, and in this case, the discrete set will be also closed and bounded. And also, well, it's not stated in the paper, but you can also show that not only is it equivalent to that, it's actually equivalent to the fact that the disjoint union and the disjoint union in the single discrete set. So if you take if you mod out by the convex holes for each set, then you get a closed, bounded, and discrete set. This is by type completeness. You can see that. So it's kind of like finite relates here to closed, bounded, and discrete. So right now, maybe I guess a little bit of a pause from, I guess, technical mathematics and just talking about philosophy of mathematics. So another quote from the sketch of a program of Grothendieck. So I guess maybe in this context, it's nice to read that he writes, thus once the necessary foundational work has been completed, there will appear not only one time theory, right, but a vast infinity ranging from the strictest of all to the one which appears, whether rightly or not, to be likely to be the vastest of all. So, okay. And now, okay, what is the strictest of all and vastest of all? Let's think about it. So, okay, so in general, o-minimality is not closed under ultra products, but we can like we define pseudo-finite structures, right? We can define pseudo-minimal structures, which are the structures which are elementarily equivalent to an ultra product of o-minimal structures, or equivalently, these structures that given a language L with an order relation, they satisfy the common theory of all o-minimal L structures. So we call this common theory of all o-minimal L structures TO-min of L, or TO-min in short, if L is understood from the context. And the models of this will be called pseudo-minimal, as in pseudo-finiteness, right, which is known to people here which do model theory, right? So yeah, and now obviously pseudo-minimality implies definable completeness, type completeness, local o-minimality, right? Because these are all first order schemes, and pseudo-minimality is the first order theory of all o-minimal structures. Yeah, these are first order schemes satisfied in all o-minimal structures. So yeah, if there are no questions or comments, I will move on. Right, so we already kind of gave a tease to what we will define as pseudo-finite set. So a definable subset in a definably complete structure, it's called pseudo-finite if it is closed, bounded, and discrete. And in a pseudo or minimal structure, we call a definable subset pseudo o-finite. So notice that there is a distinction here. If the structure expanded by that unary predicate for that set satisfies the common theory of all o-minimal structures expanded by a unary predicate. So essentially, this is an ultra product of o-minimal structures expanded by a predicate for a finite set. And Schoutens proved that in a definable complete and type complete structure, so any definable set is pseudo-finite if and only if it is discrete, right? And similarly, in a pseudo or minimal structure, so stronger than definable complete and type complete, a definable set is pseudo-finite if and only if it is pseudo-o-finite. So in the pseudo or minimal case, these definitions coincide. Okay, and right, but yeah, but still, Schoutens left some questions unknown. Namely, specifically, he also introduced this definition or this property that's called the pigeonhole principle, which you can kind of guess that the pigeonhole principle for an expansion, for an ordered structure, right, is that every pseudo-finite set, so from now on, whenever I say pseudo-finite, it's closed, bounded, and discrete, and a function from a function on that set, if it is definable and injective, then it is also surjective. So you can state it as actually every pseudo-finite set is definably Dedekind finite, right? So this holds obviously for o-minimal structures, because in o-minimal structures, any pseudo-finite set is finite, hence definitely Dedekind finite and definably Dedekind finite. And then this gives rise to kind of a series of questions and conjectures that are kind of parallel to each other by Schoutens and Fornasero. Yeah, the first one, first of all, does definable completeness with type completeness imply the pigeonhole principle? So Schoutens didn't know this. Fornasero conjectured that if we have a locally or minimal definably complete expansion of a field, then it has the pigeonhole principle. So it's kind of same question phrased as a conjecture in the language of fields. And in general, more general, Schoutens actually was interested in fully axiomatizing pseudo-minimality by some nice first order scheme. So in particular, he wanted to know whether it can be axiomatized by first order conditions on one variable formulae only. So like o-minimality is axiomatized only on definable subsets of the line, and then you get from that the whole theory of o-minimality and some decomposition, and so on and so forth on all of these same conditions. So kind of Schoutens' hope was maybe the definable completeness with type completeness is maybe some candidate for that. And first of all, he didn't know whether it applies the pigeonhole principle. So notice that the pigeonhole principle is actually not a condition on definable subsets, right? It is a condition in arity 2 because we have the function in the axiom, right? It's not only the condition on definable subset. And first of all, yeah, so there was Alex Rennett that in 2014 showed that there is no recursive axiomatization of TO-min. So he showed this in the category of fields, in the language of fields. So yeah, okay. So there is no recursive axiomatization, and definitely definable completeness and type completeness are recursive schemes. It's a recursive axiomatization, so they are not. They fail to be a candidate, but maybe still somehow, if we have the whole, we know exactly what are the definable subsets of the line, we can somehow assert local o-minimality. So yeah, let's see what the answer is. So maybe any questions or comments up until now? Guess not. Okay, so now, yeah, so the last part of the talk, I will actually give the answer to these questions. So to answer these questions, first let's go over, I used something that is called a cyclic order. I guess it is familiar for some of you. So it's kind of, if you take, right, if you take any ordered structure and you make a circle out of it, and then you put A, B, and C. If B is between A and C in the circle, then this gives you a cyclic order. And actually any cyclic order, any structure that satisfies these four axioms can be seen as just joining the plus minus infinity of an ordered structure in creating a circle, right? So we have these axioms, and yeah, as I said, if we have a linearly ordered set and we define this cyclic order external relation to be this relation, then this is a cyclic order, and we call this the cyclic order induced by the order, right? So, and now, yeah, let's move on to the structure, which actually, so there is a construction of a structure. So already, if there is a construction of a structure, you can understand that actually I will disprove this this question, right? I will prove that the answer is negative. So definable completeness with type completeness does not imply pigeonhole principle, and even a bit more. So it kind of creates right, a new distinction between different tameness properties that generalize o-minimality. So first of all, you take T1 to be the L1 theory, where L1 is this theory. So it's the order with a unary predicate Z for a definable set, and a function that will be the definable function on Z that will contradict the pigeonhole principle. And we have in that language, okay, that contains DLO, and we want Z to be closed, bounded, and discrete. Okay, that's part of the theory. And then we add we impose that F is an automorphism of the cyclic order on Z, and it's the identity outside Z if you want it to be well defined. And then it satisfies this property that means that whenever I take Z, then Fn of Z, and then Fm of Z, where m is greater than n and n is greater than 0, so the cyclic order is preserved. I'm going to also show a drawing of this in the next slide. So you can think a bit of it as like, if you take Z, okay, let's actually move to the next slide. So let's say this is the cyclic order on the structure, and then if you take F here, right, then you apply F, let's say finitely many times, you won't cross the point that you started with. So kind of orbits are, in a sense, they are kind of tamed. They are small in comparison to the whole circle. So this is what this axiom says. Yeah, maybe, okay. So yeah, and also so F kind of moves elements in a small way compared to the whole circle, but still it moves them far enough of one another so that Z and F and any finite times applying F on Z, they don't see each other. So there are infinitely many elements in Z between Z and Fn of Z. So this can be done in a closed, bounded, and discrete set in a pseudo minimal structure. Obviously, it can't be done in an o-minimal structure, but the proposition is, first of all, that it is consistent. Why? Because we can take these axioms and only taking the finite segment of the scheme, and then if you take a finite segment of the scheme, you can see that you can actually satisfy these conditions in an o-minimal structure, right? You can take, for example, just let's say Q with the order, and then add Z as a definable set, being the Cartesian product of let's say n times n for n large enough. So you have like n square elements, and then you take F to be the rotation according to the first coordinates. So F moves the elements far away enough from each other, like K far enough away from each other, but still it's small in comparison to the whole circle of Z. I hope this is clear, but maybe if there is any question or comment that I can clarify this in a way, that would be welcome now, I guess. Or maybe I'll let you digest it. I guess, yeah, so as I said, this can be obtained in an o-minimal structure with this, and you can see this on the circle. So right, so you can just pick Z to be large enough finite set, and then choose F to be moving everything small enough in comparison to the whole Z, but still large enough so that each element is moved by at least K elements. So this satisfies the whole axiom, all of the axioms from the previous slide, and then by compactness, you get a structure which is pseudo-minimal and satisfies the whole, all of the axioms. And actually how the structure looks like, well, it doesn't look like this. It doesn't look like a finite set of points. It actually, if you look at the closed circle, right, if you take the order and close it, so you have kind of a hole here in plus minus infinity, but then you have like lots of Z strings, right, because it's closed, bounded, and discrete. So every element has to have an immediate successor and predecessor. And then at some point, it starts from some point. So this is order type omega star, and this is the order type omega, where omega star is the opposite order of omega star. So it's just flipping it around. So you can see that this is the structure on that structure, and then you can take, and then if you take F to be small enough, moving small enough in comparison to the whole structure, and large enough so that each element doesn't see really its image under F or under finitely many times operating F, then you get a kind of a nice quantified elimination result that shows that actually if you take, for example, right, so if you tweak F a little, so first of all, this structure, I want to say that it is pseudo-minimal, right? It satisfies the common theory of all minimal structures, and it still satisfies, so it still satisfies the pigeonhole principle, right? Because it's pseudo-minimal. So now we want to tweak it a little bit so it won't satisfy the pseudo-minimal, the pigeonhole principle condition. So we notice that, let's say we take F on this, let's say, initial segment of Z, so some subset of this that is ordered by order type omega star. So it doesn't really matter if we start from here or from here, but it's all the same, but let's assume we start from here. So F is injective and bijective, right? And then we tweak it a little bit so that only on this, only on this, how do I cancel the drawing? Maybe if I clear. No. Okay. No. Still some. Oh, okay. Yeah. Sorry. So, so if I tweak F a little bit so that on this initial segment that is of order type omega star, it just moves F. You just change F only on this segment to move it to one. So you compose it with a successor function. So move it one element further away. This is already injective and not surjective, right? Because the bottom part is exactly the image of the top part under F. But if you tweak it a little bit, then it's still injective, but you don't have a pre-image for this first point, so it doesn't satisfy the pigeonhole principle. And by some, well, you can see by some quantifier elimination result that takes into account that, well, F was chosen exactly so that the elements don't see their image under F, and F is small enough in comparison to the whole circle. So because of this, we have a quantifier elimination result that gives us that any definable subset in this tweaked structure is also definable in the previous structure. So they have exactly the same definable subset. So obviously they are, if the first one was pseudo-minimal, so type complete and definably complete, the second one is also definably complete and type complete, and it doesn't have the pigeonhole principle. So it does not, right, so we have that so we have two structures which have the same universe, same order and same definable subsets, one being pseudo-minimal, and the second not, and not only that, not having the pigeonhole principle. So in particular, right, there is no axiomatization of pseudo-minimality by first order conditions on one variable formulae only. So not only recursive, in fact, you cannot axiomatize pseudo-minimality by any condition.
I think we need to get to the end pretty soon, okay?
Yeah, actually, this is my last slide, sorry. And okay, so relating, yeah, so this is what I stated. And relating to the questions, actually, yeah, it's a good question whether this can be done by expanding a real closed field. So I don't know, and this is something that I've had a few discussions with people about, but with no real answer, and I don't know. Hopefully in the future, I will be able to collaborate with someone in finding the answer. So anyway, thank you for listening, and sorry for the...
Okay, thank you very much. Are there any questions from the audience?
Nadav, why do you ask about the field? Was there a group around even in your structure? I missed it.
No, so yeah, it's a good question. I don't, so the thing is, I don't even know about a group, right? I don't even know about an ordered divisible abelian group. So yeah. Yeah, good point.
Any other questions?
Can I ask something kind of more general? Can these ultra products of o-minimal structures be used to look at pseudo-finite fields?
Sorry, can you repeat?
Can you use kind of pseudo o-minimal structures to analyze pseudo-finite fields? So take the reals, and then they interpret Z modulo PZ, right? Now you take an ultra product, and in an ultra product, it interprets a pseudo-finite field. So there's a measure in this pseudo-finite field, and there's this ambient o-minimal structure. Is this somehow looked at, or?
Yeah, actually, I think it's a very good question. I guess it's a good question. I haven't considered it, and I don't know if anyone actually did so. Yeah, but
Okay, well, thank you very much again for your talk. We will have a seminar a week from today, when Jean-Baptiste will be speaking. And hopefully next time I won't send out the wrong link first.
Thanks very much for having me, and just for context, to not look newly on the Grothendieck's quote without the missing parts. Now it's kind of nice to look at it in a new context, maybe.
We'll see you all next week then.
Thank you.
Thanks. Thank you.
Bye-bye.
Thank you, bye.
Bye-bye.
Thanks, bye.
Bye-bye.
Thank you.